As much as I would love to show you a cool YouTube video lab, the reality is this goes much faster, so you'll probably appreciate it more. So, we should talk about refraction calculations, and if we do a lab, we should be ready for that. And there's 2 or 3 general equations that we're going to use. And the one we talked about earlier was this relationship between the speed of light and the speed of light in a medium. So the speed of light in a vacuum, and then if it's any other medium, whether it's glass or water, plastic, and so on. And so we said that the relationship is pretty basic, that it's 3 times 10 to the 8th meters per second for light in a vacuum and pretty much air. But in a medium, it is slower. And so things that are what we call optically dense, for example, glass or plastic or water, right? We would have something like this. And so maybe light doesn't slow down too much, but this would be 1.2, right? 30 over 25. So this would have a index of refraction of 1.2, which means it doesn't bend very much. Okay? If you have the index of refraction of diamond, I want to say it's around 2 or something like that, and that's pretty significant, right? So water, I don't know, I'm just going to guess is like 1.16 or something like that. We'll call it 1.2. It doesn't bend much. Okay, so we don't see numbers much above 2. And so that's a basic idea of that equation. Then there's something called Snell's law. And it's a more extended version of what we're doing here. And it says the index of refraction in the incident medium times sine theta I equals the incident of refraction in the refracted substance, and we'll show you what that means after the light gets turned. And we have sine theta R. And this is definitely useful to memorize, maybe not when you're doing online teaching, but online learning, but definitely in a physics class. So what does all this mean? We showed you in a previous video that if light comes in, we could have any shape here. Now we are looking down. We are looking at a bird's eye view, for example. And we have shapes of plate glass that are like this. And what happens is that if the light comes in perpendicular, normal to the surface, then it goes through unchanged for reasons we're not going to get into. Maybe we will, but not here. But if it comes at an angle, for example, I drew this. Okay, now we are at an angle. It's very helpful to draw a perpendicular, right? That's the normal, so you can put N, right? And we've seen this before. What happens is, basically you could just say, well, if the light were going to go on its straight path, unchanged, that's what it would do. When we go from a less dense medium to a more dense medium, it changes direction. So here, this is air, which is basically 1 for index of refraction, right? Because it's similar to the speed of light. But here for glass, we could say, I think flint glass is something like 1.6. Okay? Either way. But it bends toward the normal. So when you go from less dense medium, it bends towards the normal. And this is one of those things you have to just get used to. So instead of going on a straight line path, I want to use a different color. We would say that it bends toward the normal, continues through, and you can observe this, by the way, just sitting in lab, if you had like a, for example, excuse me, we could have a laser, right? We could just have a pen light laser, right, shooting out a green beam, let's say, something like that. Okay, so yeah, you could have a situation where you can see this actually casting light onto the paper. But then the laser will actually change direction. So obviously here it didn't go straight, it curved, but it now does the opposite. It curves away from the normal when it goes back into the lower index of refraction. Okay, so this time we would draw, I'm going to draw it back to black. And so instead of going straight, this time it would bend away from the normal, at least a little bit noticeable, right? Because we could say, well, the green would just kind of continue on that path, something like that. So we could make that more drastic. We will in the next picture, but that's the whole idea, is that light comes through. Okay, let me show you one more before we do a very clear example. If light comes in perpendicular to this, then we don't get any refraction. Okay, but let's this time draw the normal here. Okay, we're going to draw that normal here. And the incoming light now, remember we want it to bend towards the normal, so we're going to draw it something, yeah, we could draw it like that. There's the incident light. Okay, now the thing we have to remember is where the incident angle is at. When we talked about sine theta and so on, that's right in here. This is theta incident angle. Right in there. Okay. Now we would expect that the light would travel in a straight path if it was not refracted, but in this case it did turn. It was changed in direction, and so now we'll make it a little bit more drastic here. Okay. And so there you go. And then, for example, we would see a little laser light beam that would come through. We don't really care about what happens over here, by the way. We can be totally done. Now, just as a matter of convenience, though, it wouldn't travel on its straight line path. It would bend away from the normal. So be aware, it wouldn't bend that way, right? This is the normal up here. Different normal. And you could do it this way. This is the first normal. This is the second. What's happening then is it would bend away from the normal. Okay? And it would exit there. Now, these two are not parallel. Not like you have with a situation like that. Okay? But you have this. And this actually happens in lab. But let's go back now, because the refracted angle here is this area. That's right in there. Okay, so that's the refracted angle. Okay, so what do we do? I mean, can we calculate the speed of light, or what do we do? Well, yes, absolutely. Here's how it works. You have Ni sine theta I equals Nr sine theta R. But works out, though, that we could do a couple things with this one, but because this one is air, right? This is the N equals 1 for air, because that was our incident medium, right? And we could say this one is glass or plastic. We said flint glass, which may or may not be 1.6, but we could say what that is, right? But maybe we don't know the refracted angle, for example. So as long as we have this equation, let's say we don't know that this is going to be glass. Like, we're not sure. And that's what you do in lab, is you run these trials, and then you say, well, based on the index of refraction, it's not glass, it's plastic. All right? So let's rearrange this equation here for N sub R. right? What is the index of refraction of the thing we don't know? And it should be Ni, and then sine theta I over sine theta R. Let's make sure we have that, right? Nr here, Ni on the other side, and these two over each other. But remember, this is 1, right? So now the index of refraction is sine theta I over sine theta R. And we'll just make up some angles. Excuse me. So we can say that this is sine theta. Let's go back to our diagram, though, so we know. What do we think here? Sine theta here is bigger than that. So we could call that greater than 45. We could call it 53, or let's call it 50. And we'll call that something like 27. Okay? We're totally making numbers up. We can do what we want. So 50 degrees incoming, 27 degrees leaving. Okay? So what do we have here? If I take the sine of 27 first, and then divide by 50 sine equals invert 1.68. What a good guess. Sorry, you didn't see any of that. This is 1.68. Okay, so if we have that situation, make sure you got that in your notes. Would you say that's close to the 1.6? Well, it's a 0.89% error, something like that. 1.68 minus 1.6 equals divide by 1.6 times 100, 0.5%, something like that. Very small, very small. So that's the way now you can prove, or at least determine the identity of the glass. Let's do another example here. We want to know if something is water. Okay, we want to test water. Now what you can do is, there's a tray here. Small tray that we have in lab. Okay, and you fill it with water, put it on a sheet of paper. Right, so we have this situation here. We fill this with water. Okay. And so on. All right, so there's water in that tray. You take a laser pen, if you want, if you have one, just a little guy, right? And we can direct a beam right into that. It has to be at an angle, but you get the idea, right? And so what happens is you actually get a line that comes out the other side. All right, so we're going to draw that. We're going to draw this a little bit more elaborate so you can see exactly what's going on in lab. All right. So now we have this light beam that's coming in. There's our green light that comes in. And it's always helpful. You actually need a ruler, you draw, or a protractor, and there's your normal. Okay, so there's a normal to the surface. But we know that green light is not going to go straight forward, so we're going to assume that it does, so we can see it as a reference, but it doesn't do that. It bends toward the normal, so we're going to do that, and the light turns black. We don't really care, okay? And then we can't do anything about it. Later on we would draw the normal. Here's the second normal. But it would end up being parallel. So let's just draw that. Comes out the other side. And so if you look at it, right, the incoming light here, I don't want to put an arrow there. There. Okay? These two are parallel. You can see that. Yeah? They're parallel. All right? As long as these two are parallel to each other. All right, so let's zoom in on that real close now so you have an idea. Question. How do you know how to draw that? Right? Because that's within the glass. So what you do is you draw a line where the laser beam is, right? You can just take your pencil and draw on that line. And then you draw the line on top of this one that's coming out the other side. Be real careful. Take off your metal or your glass plate and draw a connection between them, right? So that's how you do it. Is you take off that glass plate first and then put that in there. All right. So is this right? We know this is a water tray. Okay. So let's call this closer to 42 degrees, something like that. This is more like 27 degrees. We'll use 27 degrees again. Question, is that water? I don't know the index of refraction of water. I'm guessing 1.2. Okay, so what do you have here? Ni sine theta I equals Nr sine theta R. You rearrange, but remember this goes to 1, so that's not a big deal. And so now you have the index of refraction is sine theta I over sine theta R. And we're going to go with 42 and 27. Okay? So there's less of a bend here. There's less of a change. So let's try this one. Here we go. Clear? I like to do it this way, although we could sine 42 divided by the quantity of 27 sine quantity closed equals 1.47. Okay? So if water is near 1.47, then yes, we could have used alcohol, we could have used some other liquid, but that's the general idea. Okay? What you could also do is figure out the speed of light in that substance. And we know the speed of light in a vacuum is 3 times 10 to the 8th, but we have this relationship here. So what is the speed of light in that medium? This is pretty straightforward for you guys, right? Speed of light would be this over 1.47. So 3e8 over 1.47. And it comes out to be 2.03 times 10 to the 8th. Nope. So that's the velocity in that medium, which is probably water, but something like that. Okay? So those are some basic ideas about how to do the lab calculations. However, we have another topic to cover, and that is how to do the angles. In other words, expected angles. Now here's where it gets interesting. Let's take a sample of diamond. Okay? And we need to figure out the index of refraction of diamond. So let's just, we'll do a quick Google search here. And diamond is really good. Okay, so anyway, the index of refraction of diamond is 2.417. I thought it couldn't be any more than 2, but diamond is 2.417. Okay, and let's just take some regular glass. We could talk about glass and see what it is. And they're showing, yeah, they're not showing. Okay, so water is 1 point. You think they would show glass, but they're not. They're 1.52. Okay, glass is 1.52. And then we could talk about others, but for example, water is 1.33. The question in lab, or the question on calculations, will be, what will be the expected angle of refraction? None of this is going to be hard. So we get a grant, we get a huge amount of money, and we make diamonds. Okay, we have diamond here. Not really. Okay, but let's say that we have, to a very large scale, yes, this is a diamond. Okay, and we're going to test this diamond by shining light at this angle here. So that's our incident. And like I said, it's always helpful here to draw this reference line. So there's our normal. Okay. Question. If it is diamond, then what is theta r? What is the refracted angle? All right, well, we can measure this. If we wanted to, we could find that angle fairly well, and we'll just guesstimate it at 37 degrees. Okay, so that there is 37 degrees. We don't want to be too far off, so we hope that that's 37 degrees incoming. The question is, now you know that the light is not going to travel straight, okay, but because it's diamond, it's actually going to refract significantly. So let's try that. Maybe we're close, right? So theta refracted is right in there. Okay, so what do? Sine theta I and sine theta refracted. But because this is our incident and so on. But now we're not solving for that. We can do this. But now we're looking for sine theta r. So sine theta r refracted equals sine theta I over index of refraction. So we had, I'm sorry, this should be 37. There we go, 37 degrees. How about that? Okay, 37 degrees divided by the 2.417. Okay, now remember, that's going to be sine theta r. So clear? 37 sine divided by 2.417. That gives us 0.249. 0.2490. Okay, the inverse sine of that is 14.4 degrees. Okay, so theta refracted equals 14.4 degrees. None of this should be hard for physics people. Awesome physics people like yourselves. How we doing? We measure there, and haha! I love it when a plan comes together. If you can line that up there, nailed it. Thank you. Thank you very much. Thank you. That worked out pretty awesome. Okay, so that's the basic idea. Is none of this is going to get harder. The only other thing might be if you have a plate here, light comes in here, changes directions toward the normal, right, and then reflects parallel. Okay, we might be able to ask you, if this is theta refracted here, right, what is this exit angle? Stuff like that. Okay, so none of it, you just have to pay attention to the problem to make sure you know what's going on. But that is the basics. So let's walk through this as we always do in the videos. Make sure we're good. Okay, the general idea is that refraction now comes with calculations. The speed of light is greater than any other light medium, right? So the value is always going to be over 1. It turns out diamond is much greater than 2, and water is about 1.33. So we're okay with guessing. there's a concept called Snell's law, and it says the incident refraction, or the index of refraction for the incident medium times its incident angle is equal to the angle, or the index of refraction for the refracted light times that. Okay, so we did a couple problems here, and this is an example with glass, just to show you the general idea that light changes its direction. Okay, even works with odd shapes, and we could have done this with circles. Okay, but with a circle you would draw a tangent as the normal. So if light comes in here, right, you just have to draw a tangent, and that serves as your normal. So that's not going to throw anybody off. Okay, so we did some calculations and found out that if you can find the index of refraction in lab, you can test this to see if it agrees with what they say your substance is, whether it's glass, plastic, or water. Okay, another example here is just if you had a tray of water, you could use your laser for your sight lines, and if we look at this water above, right, so we set this on top of the lab sheet, right, that's full of water. We're looking down. A laser here off to the side produces a stream of light, and then when we take off this plate, we could draw that line to connect them. That's how you get in the incident angle and the refracted angle. So again, we can do the calculations. Get used to this, that air is really index of refraction of 1. And you could even figure out the speed of light, because that's usually what they do in the labs. So what's the speed of light in that substance? And you don't really need to know what the substance is. Okay. And finally, diamond is probably the best. Probably has one of the highest. There's a couple other ones like silicon carbide or titanium dioxide that are better or refract light more. Mercury sulfide and gallium phosphide. Okay, not too common. Okay, so diamond isn't the best, but it's pretty good. And so we could do that here, right? Is this diamond, or what's the angle of refraction for that substance? So that's the general idea of how to do the refraction calculations and the pre-lab.